culture, and the world around us. That's why we create opportunities for everyone to discover, discuss, and critically examine science. Through our innovative public events, world-famous Christmas lectures, and cutting-edge education programmes. In fact, we've been doing this for well over 200 years now. Help us inspire everyone to think more deeply about the place of science in our lives.
Good evening and welcome to the Royal Institution. You may notice there's no furniture behind me, so if you're worrying that the speakers didn't turn up, don't worry, they're here. We're just having a very special evening tonight for one of two reasons. One, it's our 200th and 20th birthday. Yeah! Thank you very much. So yes, the RI has been doing science communication for 220 years, and let's keep doing it for another 220 years. Thank you very much to the RI members that keep supporting us yearly, and thank you for those who are here for the first time. It's not without your support that we can't keep doing this, so I can't stop saying thank you. I've had a lot of cake today, 220 years worth. Another special reason why tonight is special is because we have a live streaming to YouTube. Ooh. So if I've looked into the right camera, hello YouTube! Welcome to the Royal Institution. For you guys at home, probably just my mum, if there are any technical difficulties, we apologise. It's the first time we're doing this. There is a good placeholder for that though, so it's enjoyable. And if you do send us your questions and comments, we will try and get those answered for you later when we do a Q&A session with the rest of the audience. So stay tuned, send us your questions and comments, and enjoy. Back to real life, because that's a bit weird. Yes, there's not much more else I can say, apart from I hope you enjoyed tonight's event. It should be a good one. And I'm going to pass over to the chair for the evening, physicist and broadcaster, Dr. Helen Czerski. So round of applause, please.
Hello. I didn't know this was a birthday party as well. That's quite cool. And it's a very appropriate topic for a birthday party because, as you will have seen, and the reason you're here is that this evening is about what might be the next good piece of technology in physics. We have heard a lot in the news over the years about CERN and the Large Hadron Collider, and it's kind of become this fixture, especially since the discovery of the Higgs boson. And it's a very visual experiment, you know, this great big circle underneath the centre of Europe for Switzerland and France, and it's a thing you can understand in it, and you can sort of imagine physics being done there. But all good experiments come to the end, and although the Large Hadron Collider still has another 15 years to go, physicists are thinking ahead. They want new physics to be working on. They want more new particles. They always want more particles, right? So there's a lot of physicists looking ahead to what might come after the Large Hadron Collider, and that's what we're going to hear about this evening, this thing that is called the Future Circular Collider. And what I like about particle physicists, apart from their ambition and the scale of their ambition, is that it seems in every other area of life, technology is getting smaller, and it's very boring, right? Phones are getting smaller, energy generators are getting smaller, everything's getting smaller so you can't see it. Not in particle physics. They had the Large Hadron Collider, 27-kilometre loop, and now what they've got in mind is even bigger than that. And to tell us about that this evening, we have two perfectly qualified guests. Please come out. We've got Harry Cliff and John Womersley. And yes, give them a round of applause. And these two, we've got the perfect combination here because, first of all, Harry's going to give us an introduction to the physics and what new physics exactly it is that anyone wants to see anyway. Like, what's the aim here? And then John is going to give us some insight into whether it might happen and how it might happen and all the sort of complications behind the scenes, which are actually really interesting when it comes to getting big collaborative physics projects done. So Harry is a particle physicist at the University of Cambridge who works at the Large Hadron Collider. John is currently the director, I have to look because it's a long title, the Director General of the European Spallation Source, which is another big physics experiment. But he's had this string of interesting jobs with big physics facilities. This idea that, you know, you need big collaborative projects to get physics done. So they are going to be our guides for this evening. So the way this is going to work is we will hear from Harry first, and then John, and then we'll have time for questions. So hold your questions until that point. If you're watching on YouTube, you can also contribute with your questions, so everyone's included here. And I think that is all I have to say. So to get us started on what all this new physics might be, Harry Cliff.
Thanks very much for that introduction, Helen. So someone asked me today, is the LHC clapped out? Is it finished? Is that why you're planning the next one? I'm going to say no, because my job for the next 15 years at least depends on it. The LHC is definitely not clapped out. But what we are here to talk about tonight is what hopefully might come after this amazing machine. So just in case you haven't met the Large Hadron Collider, here it is. This is an aerial shot taken from the sort of direction of the Jura Mountains looking north towards the Alps. And you can see Lake Geneva there, that grey smudge in the distance is the city of Geneva. That big high mountain is Mont Blanc, and then marked in yellow on the countryside is the root of the biggest scientific instrument that's ever been built by human beings, the Large Hadron Collider. So this is where I work, and this machine, in a way, particle physics is the sort of simplest, most brutal thing you can think about doing scientifically. We want to know what things are made of, so what do? Well, we take projectiles, we whiz them around very, very fast, we smash them into each other, and we see what happens. And that's what this machine does. So at some point over here at CERN, there is a bottle of ordinary hydrogen gas. The hydrogen is ionized to produce protons. The protons are whizzed around a series of accelerators, which were sort of at one point the biggest at CERN, back particularly this one called the super proton synchrotron, which used to be the biggest particle accelerator in the world, the most powerful one in the 1980s, and then it goes into the LHC. They go round and round in a circle. They're accelerated to 99.999991% of the speed of light, and then they collide into each other in 4 detectors, which are spaced around the ring. And when that happens, this is what you get. Particle colliders, what they really do is they probe the structure of the universe, the structure of reality at the shortest distance possible. So this is in a way acting like a gigantic microscope. And when you have this much energy loaded onto these protons, when they collide, that kinetic energy, the energy of their motion, is converted into new particles. So what you're seeing here are not the innards of the proton necessarily, although they are mixed up in this picture, but actually particles being created out of energy that didn't exist before. And then people like me scan through trillions and trillions of these sorts of collisions in search of signs of new particles like the Higgs boson. So that's what the LHC does, and that's what all particle accelerators do. So, and as I said, this machine has quite a long life still ahead of it, and we're hoping that the LHC will deliver some exciting discoveries still in the coming years. But the reason we're already thinking about what comes after is the actual first sort of conversations about building the Large Hadron Collider took place in the late 1970s. The LHC didn't start colliding until 2009. So that gives you a sense of the timescales involved in these projects. So if you want to have a machine ready for when the LHC switches off, we need to start planning it now. So the big news, as Helen mentioned in her intro, that's come out of the LHC so far is the discovery of a particle that was first predicted in the mid-1960s, which is known as the Higgs boson. And I'll talk about it a bit more later on in the talk, but very briefly, what this discovery tells us is that there is an invisible energy field everywhere in the universe. It's in this room right now. It's called the Higgs field, and it's this field that gives mass to the elementary particles that make up the universe. And that's the great triumph of the LHC so far. And it's also sort of, in a way, this discovery finished the 20th century sort of model of particle physics known as the Standard Model. So this is our current best description of what the universe is made out of and the forces that bind the different elementary particles together. So I'll very quickly just introduce you to some of the particles in this table, just so you know when I use words like quark, you know what I'm talking about. So first of all, we have the electron, which is the particle that goes around the outside of atoms. It's negatively charged. And then we have 2 quarks called the up quark and the down quark. And these make up the nuclei of atoms. So these are the 3 basic ingredients of all the ordinary matter in the universe. That's all we are. We're just made of electrons and these 2 quarks arranged in a variety of different ways. And then there's a bunch of other particles. There's one called a neutrino, and these are sort of like ghostly things that are going through us. There are trillions of them actually going through your body right now, but you're not aware of them because they very, very rarely interact with ordinary matter. And then for some reason which we don't understand, nature provides us with additional copies of these particles. So these are 2 extra columns in this table, which have more or less the same properties as the electron and the quarks, but they're heavier and they're unstable. So you can make these exotic particles in collider experiments, for example, but they don't hang around very long. They quickly decay down into what we call the first generation in this table. Then there are a bunch of particles which are associated with the different forces of nature. So there are 3 forces in the standard model of particle physics. One which is missing, which is gravity, but the 3 quantum forces, which are the electromagnetic force, and there's a particle called the photon, which transmits that. And then there's the strong nuclear force, which binds the quarks together inside the nucleus of an atom, and that has a force carrier called the gluon. Because it's gluey, it sticks these quarks together. And then there are some weird particles called the Z and the W boson, which are, these are the particles that transmit a force called the weak nuclear force, which is associated with radioactive decay and when one type of particle transforms into another. So that's more or less all of particle physics in about a minute or so. And then this was the picture of our understanding of the universe on the 3rd of July 2012. And then on the 4th of July, Higgs Dependence Day, CERN announced the discovery of the final piece of this puzzle, the Higgs boson. So the discovery of the Higgs was really at the end of the story of the Standard Model in some sense, the last missing piece of this theory. Now, that's not to say, though, that the Standard Model is the end of the story. We know that there are many problems in fundamental physics, some really deep and mysterious problems that the Standard Model just cannot address. And one of them is to do with a sort of a mirror image of the ordinary particles, the ordinary matter particles, something you may have heard of called antimatter. So every particle, every matter particle in the Standard Model, the quarks, the electrons and the neutrinos, have a mirror image which has exactly the same properties but the opposite electric charge, and we call these antiparticles. And we've known about antiparticles since the 1930s, and they're routinely created in experiments, and their properties are understood very well. But one of the problems with the Standard Model is that it tells us that whenever we create a particle, we also create an antiparticle at the same time. And if you use this sort of logic to understand the beginnings of the universe, what happened at a very early time, sort of a trillionth of a second after the Big Bang, you had huge amounts of energy being converted into matter and antimatter. And these 2 forms of matter were kind of being created and annihilated repeatedly. And as the universe expanded and cooled, the matter and the antimatter met up and annihilated each other. Now, because the Standard Model says whenever you make a particle, you have to make an antiparticle, and whenever you annihilate a particle, you have to annihilate an antiparticle, what should have happened is that these 2 equal quantities of matter and antimatter should have totally annihilated each other and left us with an empty, dark, lifeless universe. But that's not the universe we find ourselves living in, fortunately. So the universe has got lots of stuff in it, and so we don't understand how this happened. How is it that enough matter got left over after the Big Bang to create all the stuff that we see around us? This is a really big problem for the Standard Model. So we know there must be some new physics to explain what happened very early on in the history of the universe that allowed this little imbalance to occur. Another big problem is actually, so there's a clue to it in this image. So this is a shot of a cluster of galaxies called the Abell cluster. It's a big collection of galaxies sort of hanging about together in deep space. And if you look very closely at this image, you hopefully see that there's a sort of circular smearing pattern. This is the cluster in the middle. You see all these bright blobs, which are galaxies. And then there's this circular smearing that you can kind of see, almost like a kind of a lens in between us and those galaxies. And this is actually an effect known as gravitational lensing, which is where the mass of these galaxies are bending space-time, and they cause light as it travels through the universe to be bent, just like an ordinary lens. You literally get a sort of a lens appearing in the sky. Now, the amount of bending of the light that you get depends on how much mass there is in this image. So you can do 2 things. First of all, you can look at how much visible material there is, how many galaxies, how much dust, and you can figure out how much mass there is. And then you can look at the lensing and figure out how much mass that says there is. And these 2 numbers don't agree with each other. and they don't agree with each other by a very large amount. The amount of lensing that we see requires more or less 5 times the amount of visible matter that we can see in this picture. In other words, there's some invisible matter which we can't see, which is creating extra gravity, extra bending of space-time, and this is what we call dark matter. You can even use this to actually map dark matter. So this is in purple. Purple, for some reason, is the color of dark matter, and it's overlaid on this image. And this shows you that there's a lot more stuff than we can see with our telescopes. Again, the standard model has no explanation for dark matter. There is no particle in that table that I just showed you which can account for this. We know some things about dark matter. We know that it can't interact through the electromagnetic force because we'd see it would give off light, and it can't interact with a strong force, but it might interact with a weak force, but that's more or less all we know about it, and the standard model can't explain it. This is a sort of picture of what we think the universe is made from. So here we have atoms, so that's us. So all the stuff that we've been studying in all of physics since we started doing this is only actually 5% of the universe. We've only really scratched the surface in terms of our understanding of what the universe is made out of. 27% is dark matter, which is this mysterious substance. We think it's a particle, but we're not too sure. And then there's something even more mysterious called dark energy, which is some kind of repulsive force that's causing the universe to expand at an ever-accelerating rate. And basically, what this picture tells you is that whenever you hear the word dark in physics, it's a sign that we don't know what we're talking about. So as I said, the standard model, and the standard model itself actually, has some mysteries about it. So this table may sort of slightly remind you of the periodic table of the chemical elements, where you have these repeating patterns. We don't understand why there are 3 columns here. We don't know why they exist. They just are there. We just kind of say, oh, we observe them, we put them into the theory. And we don't really know why we have the particular forces we do. Nature could have chosen a different set of particles and a different set of forces. So we'd also like to be able to understand where this picture comes from. And the Higgs itself is also a mystery in some ways. There's lots we don't understand about the Higgs boson. Although the Higgs was discovered, almost 7 years ago now, we've managed to measure some of its properties at the Large Hadron Collider, but only quite imprecisely. So it looks very much like the Higgs boson that Peter Higgs and his colleagues predicted in the 60s, but there's still a strong possibility that it's not the standard Higgs boson, that it's something more exotic. And we have to study this thing more precisely to really figure out if that's true or not. So as I said, the LHC has got a program that's going to take it through until 2035, and we're still very hopeful that it may discover new physics that could help it tackle some of these problems. But whether it does or not, it's very unlikely to be able to solve everything. We're still going to have unsolved questions at the end of this process, although what the LHC does discover in that time will to some extent dictate what comes after it, because we'll probably build a machine that helps us probe the things that we've got the most evidence for. So this is the proposal. So this is a map of what could become the successor to the LHC, the Future Circular Collider. So it's a proposal for a 100-kilometer circumference tunnel. You can see here's the LHC up here, and the LHC would now be acting as a sort of a feeder, a sort of motorway slipway, which would inject particles into this much, much larger ring. And the reason we want to go bigger is the bigger the collider, the more powerful, the higher the energy you can get the particles to, and that means that you can make more massive particles. So it could be, for example, that the particle that accounts for dark matter is too heavy for the LHC to make. But so in which case we will need a bigger machine to be able to produce these things. This is a sort of a nice visualization of what you might see if you went down into the tunnel. I assume it's not all going to be covered in chrome, but it looks really futuristic and space agey. Anyway, so that's your accelerator. That's the tube that carries the particles. And then, just like at the LHC, there will be caverns around this ring where the particles are brought together and they will collide inside gigantic particle detectors that may or may not look a bit like this. And these are sort of essentially huge three-dimensional digital cameras that record what happens in the collisions. So very similar to the LHC, but on a bigger scale. So I'm going to briefly say a bit about the more specifically what this machine may end up being like. There's actually what's called the Future Circular Collider is really a proposal for two different machines, and as which one gets built in which order will depend in some part on what happens at the LHC in the next few years. But the first sort of phase of this project is for an electron-positron collider. So this is an accelerator that collides electrons with their antimatter versions called positrons or anti-electrons. Now, these machines are really great for doing precision measurements because you have these two fundamental particles, you know exactly what their energy is, and when they collide, they annihilate perfectly, and then convert into Higgs bosons or whatever it is that you're interested in looking for. And that means you have, they're very, very good. For example, if you want to measure the properties of the Higgs boson at high precision, oh dear, things falling over there. If you want to measure the Higgs boson at high precision, this kind of machine is great for doing that. The problem with electron-positron colliders is that when you make an electron accelerate in a circle, it gives off X-ray radiation called synchrotron radiation. And the more you accelerate them, the faster they radiate their energy away. And so this is actually used at facilities like Diamond, where they use the X-rays that come off accelerating beams of electrons to study the structures of materials. But for a particle accelerator where we want to collide things, it's a real problem because it becomes very difficult to get the electrons to very high energies. So electron-positron colliders tend to have lower collision energies, but they're very good for doing precision measurements. Then you have proton-proton colliders like the Large Hadron Collider. Now, the advantage of proton-proton colliders is that protons are much heavier than electrons, and that means that they radiate they give off these X-rays at a much lower rate than electron-positron colliders, and consequently, you can get these protons to much, much higher energies. They're very good if you want to reach out into sort of the high-energy world and create very heavy particles. The disadvantage is that protons are they're not fundamental particles, they're messy bags of quarks and gluons. When you smash them into each other, you get a whole lot of mess just all over the place. So this is a typical image from the ATLAS experiment at CERN, at the LHC, and you can see the number of tracks that are being created in this collision. It's trying to find a Higgs boson in this, for example, it's sort of like trying to find a needle in an exploding haystack. It's really a nightmare. So there's much higher background. So they're good in terms of getting to high energy, but there are big challenges in terms of analyzing the data. And you have to use very clever techniques to sift out the stuff you're interested in. Another problem, in a sense, this is a photo of the LHC. Because these protons are massive and they're going at very high speeds, you need incredibly strong magnets to bend these particles around the ring. And those magnets are also very expensive. So these colliders tend to be slightly more pricey than electron-positron colliders. So there's two proposals, as I said. I'm just going to show you, just take you very briefly through the history of some accelerators at CERN, so you understand the interplay of these two different types of machine. So back in the 1980s, the most powerful accelerator at CERN was the super proton synchrotron. It was 7 kilometers in circumference. It got particles up to an energy of what's called 400 giga-electron volts. So that is that energy is equivalent to the amount of energy carried by an electron if you accelerate it through 400 billion volts. That's the kind of typical unit we use in particle physics. To give you a sense, the mass of a proton is 1 giga-electron volt. So this accelerator in principle could make something 400 times heavier than a proton. Then, so what happened at the superproton synchrotron is that this is a hadron collider. It's a proton-proton collider, which is very good for discovering new things, and indeed it did make some really exciting discoveries. It discovered what are known as the W and the Z bosons, which are the force particles of the weak force. They've been predicted by theory in the 1970s. This was a really exciting time. This was in the mid-1980s. Then after the superproton synchrotron, CERN built a machine called the Large Electron-Positron Collider, which was a 27-kilometer particle accelerator. It's actually the tunnel that the LHC is in was built for this machine. And what the Large Electron-Positron Collider did, because it was colliding these elementary particles with each other, is it could measure the properties of the W and the Z particles very precisely. So the SPS discovered them, but then the Large Electron-Positron Collider could really pin down their properties in a lot of detail and tell us lots of interesting things about the nature of the weak force and also about the standard model. And then after the Large Electron-Positron Collider switched off in the year 2000, work on the Large Hadron Collider began, and it was eventually brought online successfully in 2009 in the same tunnel, but you can see the difference in energy. So you go from 400 giga-electron volts to 209 for the Large Electron Positron Collider, and that's because of this problem with electrons radiating all their energy away, and then you get to much higher energies with the Large Hadron Collider, 13 tera-electron volts, so trillion electron volts. And then this machine, as a discovery machine, discovered a new particle, which is the Higgs boson. So this is the general pattern that's been established at CERN, at least in the last few decades. The plan for the future circular collider, the sort of standard view would be, the first phase would be to build an 100-kilometer tunnel in which you would put an electron-positron machine. And the objective of this machine would be to study the Higgs at very high precision. And then after that, you would have a much more powerful hadron collider going up to about 100 tera-electron volts. And that would be the machine that could really give you the best chance of discovering brand new particles. Right, in the next, 5 minutes or so, 6-7 minutes, I'm going to have to try and explain the actual physics of these things. So what would we want to do? Well, at the electron-positron collider, what this machine would allow us to do is to study the properties of the Higgs boson at really, really high precision. And this is interesting because the Higgs is actually a really unique particle in the standard model. It's the only particle in the standard model which has no spin. So all the other particles behave as if they're spinning around. The Higgs is spinless, and this gives it a unique set of properties and a unique set of theoretical problems associated with it. To give you an example of what these kind of measurements could do, there's a possibility that the Higgs boson could act as a sort of gateway between the ordinary matter in the standard model and what we call the dark sector or the hidden sector. So this is the world of dark matter. So if you can imagine, you have the standard model over here, and then separated because it doesn't interact with any of the forces in the standard model, you have dark matter, this kind of parallel universe, effectively, of stuff that we can't touch or see. Well, there's a possibility that the Higgs boson acts as a kind of gateway, so it interacts with the standard model particles, but also with this hidden sector. And so by measuring its properties very precisely, you can detect evidence of it interacting with these dark matter particles. So it would be a way of indirectly finding evidence of the existence of dark matter. Another possibility, so again at the electron-positron collider, the way that Higgs bosons will be made is sort of goes something like this. So you have your electron, you accelerate it to very high energy, and you bang it into a positron, they annihilate, and you produce together a Z boson and a Higgs boson. Now, again, if the Higgs interacts with dark matter particles, sometimes when you make a Higgs boson, instead of decaying into ordinary particles in the standard model, it will decay into dark matter particles. So you end up with the Higgs decaying into, say, 2 dark matter particles. Now, the problem with dark matter particles is you can't see them. So they will just fly out of your detector, leaving no trace. But because you have this Z boson here, which you do see, you're able to figure out there's some missing energy because something invisible has gone shooting off in this direction, and we've got something that we can see over here. And that would allow us, again, to indirectly detect evidence of dark matter. So one of the really sort of exciting prospects, and this is something for the big machine, this is for the Hadron Collider, the Proton-Proton Collider, is to do with something called the Higgs field itself. So in particle physics, we don't actually think of particles as little sort of billiard balls or Lego bricks. The actual building blocks of the universe are fields. So, for example, the electromagnetic field, which is filling this room. Now, a photon, which is the particle of the electromagnetic field, is thought of as a little vibration, a little ripple moving about in this field. In the same way, the Higgs boson is a little ripple moving about in this Higgs field that fills the entire universe. Now, the Higgs field is unique among all the fields in the standard model in that if you take a bit of space and you get rid of all the particles, so you remove all the atoms, all the electrons, all the protons and neutrons, then the values of all the other fields, like the electromagnetic field, the electron field, they have values that are very, very close to zero, except for some little quantum fluctuations. But the Higgs field has a fixed value everywhere in space. It has a kind of a non-zero value. And it's this non-zero value that causes this property, which we call mass, to exist. Now, the Higgs field effectively switched on at a very early point in the universe. There was a phase transition where the Higgs field went from having no value to acquiring the value it now does. And at that moment, about a trillionth of a second after the Big Bang, all the particles in the Standard Model suddenly acquired mass as the Higgs field switched on. So I said it's a phase transition. You can think of it a little bit like water droplets forming. So in this very early phase in the universe's history, you can almost think of sort of pre this phase transition, the Higgs field is a bit like a gas, and then it condenses into sort of a liquid, effectively, in different places in the universe. And there are some ideas that the asymmetry between matter and antimatter that we see in the universe happened when the Higgs field switched on in the very early universe. So if we can study this phase transition when the Higgs field acquired the value that it now does, we may be able to explain the matter-antimatter asymmetry that we see. In other words, we'll be able to answer the question, why is there stuff in the universe? And the thing that's really exciting about the proton-proton collider is because it will be able to reach these incredible energies, 100 trillion electron volts, it will recreate the energy conditions that existed at this very early time just after the Big Bang. And if the Higgs field is implicated in why there's stuff in the universe, then we will hopefully be able to measure its behavior and see whether we can explain the difference between matter and antimatter that we see in the universe through the Higgs field. One other thing, another possibility at the proton-proton collider is again to do with dark matter. So the measurements I mentioned at the electron-positron collider were mostly indirect. So they were kind of, you see sort of evidence of something through the properties of the Higgs boson. Now, this is a picture which represents the distribution of dark matter in a typical galaxy. So a galaxy like the Milky Way, for example, is a spiral galaxy, which is a relatively thin circular disk. And from looking at the way that stars and galaxies move around, astronomers estimate that each galaxy is surrounded by a halo of dark matter. And the most popular explanation for what dark matter is over the last few years has been something called a WIMP, which stands for weakly interacting massive particle. So what that basically means is it's some kind of particle, which is often given the symbol chi for some reason, which has no electric charge, but interacts through the weak force. So it sort of these things are floating about in a diffuse cloud surrounding the galaxy, and this is the kind of the most popular, the most studied form of dark matter. And the thing that's really exciting, another thing that's very exciting about the proton-proton collider is that because it can reach such high energy, it will be able to more or less explore the entire energy regime where we think these kind of WIMPs ought to exist. In other words, it will be able either to discover dark matter particles, these WIMP particles, or rule out their existence, in which case we'll know that dark matter needs to be something else, some other type of particle that isn't a WIMP, effectively. I'll just very quickly plug something. So this is my experiment at the Large Hadron Collider, or at least the experiment that I'm a part of. There are about 1,000 people working on it. It's called LHCb. And in the last few years, LHCb has seen a number of interesting deviations from the Standard Model, none of them yet big enough to really conclusively say that we've seen new physics. But when our results are finally updated with more data, hopefully what we'll find is, if these results are confirmed, they will be indirect evidence of some high-energy particles coming in and interfering with the way that the Standard Model particles behave. And it's very likely that if these effects are confirmed, and I don't know whether they will be or not, that the particles responsible for these deviations will only be accessible by a machine more powerful than the Large Hadron Colliders. This is another sort of reason why we would need to go out and build this bigger machine. I'll just finish off finally by saying there's also possibly the most sort of tantalizing prospect is that we discover something totally unexpected. Whenever we've built a new particle accelerator, we found something new. And quite often the biggest breakthroughs in our understanding of nature come when we get a result that we really didn't see coming. So, and there's a very good chance, because these machines will explore this unexplored region of the subatomic world, that we'll find something totally unexpected, and in which case that could have a really revolutionary effect on our understanding of the structure of reality. And just to re-emphasize the point I made at the beginning, that we only actually, with the standard model, have been studying 5% of the universe. We've only really scratched the surface. We're at the beginning, really, of a journey towards, hopefully, a fuller understanding of the universe. And the Future Circular Collider is one of the best tools that we could have to continue that journey of exploration. Thank you very much.
Thank you, Harry. So let your brains kind of settle down a bit. It's a lot of stuff, isn't it? And I just wanted to tell you something while I remembered at the end of Harry's talk there, is I went to visit the Gran Sasso lab in Italy in October last year, which is one of the dark matter detectors. And I went with my sister, who is not a physicist, but she came along and they gave us a tour of the lab. And it's you saw these great big machines, and they were describing all these things in Italian because they hadn't told us that the tour was in Italian. They took us around. And I understood the physics, and it turns out the words for electron and positron are the same. So I was kind of following along the physics, speaking of French and Spanish, kind of get by. And she was just listening to the Italian. She's all very musical, and she liked that. And afterwards, she said, "What are wimps? Why are they looking for wimps?" And she'd been listening to this description of particle physics, this beautiful Italian melodic language with wimps popping up. And that's her entire impression of particle physics now. So that's the big idea, right? The dreams of particle physics always after new physics. So you've had your introduction to the new physics there might be. And then there's the practicality. How do you actually do it? And John is going to tell us.
Yes, thank you very much. So, minds blown slightly. I hope, if it was up to a vote of people in this room, you would probably say, yeah, this sounds like an interesting thing. Let's figure out how to do it. Can we just see a vote of hands as good? Because you've paid money to come here and hear about it, you're obviously a biased audience. But not everybody would agree with you, certainly not at the beginning. And so we need to think about how to make the case for a very large investment in scientific research like the next big collider. And we need to do it in a way that a skeptical audience, not just an audience of enthusiastic smiling faces. So there is a sort of checklist that one can refer to for big science projects, and I'll take us through that as we get ready for takeoff with a big project like this. So your pilot is in the cockpit, and in building any big science mega project, the pilot's checklist has to go through a number of key requirements. Harry has outlined the science case, the reason why you would do such a thing, but there's a number of reasons how, or things that need to be in place for the how. And it's part of the success of big science in particle physics, in astronomy, in space research, in the Human Genome Project, all of these very ambitious things, to be able to marry a visionary goal driven by science with the resources and the organization and the engineering and the R&D and the technical capability to actually deliver on it. Not just an aspiration like hoping one day we will cure cancer, though I very much hope we will, but a practical goal like putting a person on the moon by the end of the 1960s. So that's what we're trying to do here. Technical case, cost estimates, project management plan, funding, governance, stakeholder engagement, and something called a business case, which is basically what you would tell the Treasury if you had 30 seconds of pitch with the Chancellor of the Exchequer to say this is a good investment for the public purse, for the taxpayer. So this is my current project, which is dramatically smaller. It's only 1 kilometer long. It is, however, a particle accelerator and will be more powerful than anything at CERN when it starts operating. This is a machine for material science research. This is a spin-off from particle physics, and I'm responsible for the construction of this. It's roughly £2 billion project under construction in Sweden, of which the UK is a proud member, a European collaboration to build a new science facility. before being responsible for this, I was the chief executive of the Science and Technology Facilities Council, which is the funding agency, the research council in the United Kingdom that's responsible for basic research in areas like particle physics and nuclear physics and space. So I do have some experience with skeptical audiences in the Treasury and elsewhere, and I hope that that experience can be useful to the FCC. I'm a member of the International Steering Committee for this project, and I would love to see it succeed. So Harry's talked about the science, but if you had to condense that to one slide, people in America talk about an elevator pitch. Imagine you are in a lift with a decision maker and you have 30 seconds between getting on at the floor you got on at and getting off at the floor you both get off at. How would you condense your story into a very, very short number of bullet points? So here I've attempted to condense Harry's presentation into one slide. We found the Higgs boson. It was the last piece of the 20th century jigsaw puzzle, but nature has put more pieces out there. Dark matter was never predicted in the Standard Model, but the observations in big telescopes and the Hubble Space Telescope prove that it's there. We don't know what underlies that. There are two approaches to discovery then. High precision, which the electron-positron collider in the FCC tunnel would be able to deliver, measure what you know about very precisely, and the brute force approach of a very much higher energy collider to try to directly ask nature, what are you made of? Can we make new things like we were able to make the Higgs boson at the LHC that we didn't know about so far? Now, CERN has stewardship of a strategy for particle physics, which attempts to organize all of the European laboratories that are active in this area of research and the scientists in the various universities every 5 years to update the investment plan and the research plan for Europe. And clearly, since the last time this process was carried out, we've learned a lot more about the Higgs. We've continued to do experiments at the LHC, and it's timely to do an update. So February last year, there was a call for scientific input, and the conceptual design of the FCC, which we're talking about, is one of the inputs into this strategy process. We hope that the strategy symposium and then the 5-year sort of master plan, which is not a very dense document, it's a few pages, but it lays out the priorities for investment. We hope that that will endorse continuing to take the FCC project forward as one of the priorities. Because, as Harry has said, the investment timelines are long, the R&D may take a decade to do, and if things don't get started now, particle physics could be left in the 2020s without a clear plan for what to do next. There are, however, some other competing options, and we can talk about that in the Q&A if you like. So, science case is there. The technical case and the R&D needed and the cost estimation, well, let's just put the cost numbers up there because they are large and nobody would deny that these are expensive investments. So for the first phase, the electron-positron machine, the estimate with engineering consultancy and serious study is something like 12 billion Swiss francs. We costed it in Swiss francs because the assumption is that the bulk of the money would be spent at CERN. And the dominant cost is the cost of the tunnel. 100 kilometers of tunnel, 62 miles of tunnel is an expensive thing. So that drives the cost, and that tells you what you are not likely to be able to spend less than. To go then to upgrade to the second phase will cost you an additional 17 billion Swiss francs, of which 11 is for superconducting magnets, as Harry said. Keeping the rings of the protons circulating in even this very large tunnel requires a very high magnetic field. And the whole program, which might be spent over 35 years or more, is then 29 billion Swiss francs, or 24 billion if you skip the first course and just go straight to the main course. So the two major technologies that we need to think about are the tunnel and these high field magnets. This is an overlay again of the tunnel on the Swiss-French border, just to show the sheer scale of the thing. 100 kilometers, 62 miles in circumference. That means 20 miles across, stretches from here to roughly Heathrow Airport. This is a very big engineering challenge in itself. The land is not hugely mountainous. This is the end of Lake Geneva, where the Rhone River starts, so it's not a hugely deep tunnel excavation, and that means you can sink about 16 shafts around the circumference of the tunnel, which makes it quicker and easier to build, but tunnels are not simple. Here's another, that picture, that visualization. I think this is way too Star Trek for real life. It will be a concrete tunnel. The point I just wanted to make here is the size of it is not huge, but it has to be roughly twice the width of the magnets that you want to put in there so that you can transport them in and install them, and so that one can access for repairs. A good example of 100 kilometers of tunnel in Switzerland has been excavated in the last few years. The Gotthard Base Tunnel, which is a railway tunnel, 2 57-kilometer bores under the Alps linking Zurich with Milan. That cost 12.2 billion Swiss francs. Tunneling is a mature technology. It's understood. It's not simple. The geology makes things complicated. It can be dangerous, but it's predictable. And it's unlikely that there will be any dramatic breakthroughs in tunneling that would reduce the cost or time taken to do that. So the cost of digging a 100-kilometer tunnel and the time taken to do it is understandable, and we need to be sensible about it. The other technology, however, needs much more R&D. And that's one reason why the second phase of the FCC may well come as the second phase. It requires magnets, superconducting magnets, so that means they're cooled to a few degrees above absolute zero, so there's no electrical resistance in the wires. You have to use special materials to have that property of being superconducting, and we want to run this machine with collision energies that are something like 7 to 10 times higher than the LHC. And that means having a higher magnetic field to bend the particle beams and keep them circulating in the tunnel. And we're looking for 16 Tesla magnets, compared with roughly, one Tesla for typical everyday applications. And that means new materials. We will have to use an alloy of niobium and tin, which is a very difficult material to work with. It requires a lot of heat treatment, and maybe high-temperature superconductors, which are even more difficult to work with, ceramic materials, more exotic materials, not used because of operating at a higher temperature, but because they can withstand higher magnetic fields and still remain superconducting. Expensive, costly, and an engineering challenge. We need to reduce the cost by a factor of 3 to 5 compared with existing technology used at the LHC. Now, a project management plan for a 20 to 30 billion franc project is not optional, it is mandatory, and there are good examples of engineering project management to be found everywhere in the world of big projects. For example, the American Department of Energy has a very well-respected project management approach based on that used at NASA. It's DOE Order 413B, and those of us who've worked in American labs know exactly the steps needed. But the key points in managing any big project are to have a proper schedule with tasks. At the ESS, at my project, we have 24,000 tasks linked in a project management tool called Primavera. So we know when every job finishes, what other jobs are depending on it to start. We know how many people should be working on it, and we can track the progress exactly through. And ESS is now 58% complete, according to that measure. We need sufficient contingency, money kept back for things that you haven't predicted, because your initial estimates are never fully accurate, and you need to deal with them, and you need an engineering change control process to keep track of what you're doing. Credible funding and governance plan. So if you go and talk, if you had that elevator ride with the Chancellor of the Exchequer or the Science Minister of Germany or any of the people we would need to invest in this, you want not just to reassure them that you know how to do the project, you need to tell them how you're going to pay for it and how much they would have to pay. And these get to be tricky negotiations, and they're very political. So let me emphasize at this point that what I say is not official CERN policy, and it's not necessarily even official FCC policy. It's my advice as a private citizen on how you might be able to build something of this size and complexity by involving all of the people that you need to involve. So the first thing is to look at existing examples of what we're trying to do. And the closest thing I could find is the International Fusion Project, ITER, which is under construction in the south of France. This deserves an RI presentation of its own, to build a very, very large magnetic confinement system in which you can replicate the nuclear reactions that are taking place that power the sun and try to capture that as an energy source on Earth. This is a 20 to 30 to much more billion project. The actual cost is a little bit obscure. It is an international organization, but it involves many agencies from projects all around, from countries all around the world, and there are huge challenges in building something of this size with this scale of collaboration, which have led to some lessons that ITER itself has learned about what not to do. So any project like FCC should learn what not to do and copy what does work. Oops, I keep pressing that too much. So this is the key question then that you'd have to satisfy the Chancellor of the Exchequer or the German Science Minister. Could you actually afford 28 billion Swiss francs? The Swiss franc is about 85 pence or something like that. So it's not so different from the cost of HS2 or something like that. It is a big investment. Well, the best way to do that is to spread it over many years and to share it between many partners, and that's exactly what we would propose to do here. The existing CERN budget, to which the UK contributes about £130 million per year, could pay for roughly half of the cost of this FCC program over the 30 years that it would take to realize, without asking for any more money. So you'd simply have to convince the Chancellor of the Exchequer that CERN was continuing to be a good investment for the UK taxpayer over that period. And I hope that's a more straightforward thing to do. And I don't want to have to appeal to this lady here, the magic money fairy, to say that we will, find money from a Silicon Valley billionaire or something like that. I think it's fair to ask the two host countries, Switzerland and France, to contribute a bit extra, because a lot of the money of that tunneling will be spent in their countries, on their companies, in their economy. And then the third thing that we need to do is get contributions from outside of Europe in the same way that ITER has done. A substantial investment from the United States and Russia and China and Japan and wherever else. And that means most of that work would need to be done in those places, because the Russians, the Chinese, the Indians, the Americans are unlikely to just write a check to CERN and say, spend the money in Switzerland as you wish. They're going to want to do the work at home, because as has long been noted, politics is local. People get elected by local constituencies, and they want to be able to demonstrate a return on that investment locally. So that's what we're having to do in my project at ESS as well. Significant technical work packages procured or constructed in the partner countries and then brought to the project to be integrated. It's a project management challenge, but it's a political necessity, and I think FCC is going to need to handle this. This is an example of an in-kind deliverable at ESS. You probably don't know who either of these gentlemen on the right are. Does anybody wish to guess? No, they're obscure. It's the President of Italy, and I can forgive you for not knowing who he is, and the King of Sweden, and I can forgive you for not knowing who he is either. But they're shaking hands because the King of Sweden is ceremonially accepting this component that has been built in Italy for ESS, and this means that the Italians can spend money in their own national laboratories promoting their own science and engineering investments, but contribute to a European project which is taking place in another country. Stakeholder engagement. You are stakeholders in this project. The general public are a key part of it, but there are many other stakeholders. And earlier in my life, I had the privilege of working on this project, the Superconducting Super Collider, which was about 1/3 finished in a place called Waxahachie, Texas. And yes, that is a real place. And it is exactly like you would think it would be. Pickup trucks and big hair. Well, it was the 1980s, and 10-gallon hats. And you aren't from round here, boy, are you? But a basically larger and more powerful version of the Large Hadron Collider got about 1/3 complete, and you can see big tunnels dug and real money spent. And it was then cancelled by the American Congress in 1993. And that had to do with changing political priorities, but it was evidence that there wasn't a strong and deep base of support for this big investment, and it was a political baby of one political party, and even very big projects can get killed. So I don't want to repeat this experience, and I don't think science should. We've done some studies in Europe on large research infrastructures in a forum that I've chaired, and we found that stakeholder engagement and the funding plan are often the reason why things don't get built, not the lack of science case or the technical R&D. So stakeholders include you, the general public, but they also include decision makers, the people who shape opinion. They include scientists in other research fields. They include university bosses, civil servants, and economists. And you might think that the toughest and most skeptical audience here would be the the civil service economists in the Exchequer, and they're pretty tough. But actually, the most skeptical and hardest to convince are often scientists in other research fields who are worried about whether this investment may draw money out of theirs. And those are people we need to work on. And if you've been following FCC in the media and on Twitter, you will have seen that there are people from other science areas who say this is a very expensive thing and we're not sure what it will do. So we need to convince all of these. And in fact, if we have many partner countries, there needs to be an effort to convince the people in each of those partner countries, because they have different media, they have different political parties, they have different decision-making priorities. And finally, business case. Business case is what the Treasury down the road in Whitehall talk about when they want to make an investment. It doesn't mean it has to have anything to do with business, but it just means they have to be able to justify a return on the investment of taxpayer money. And continued investment in CERN, even if it is still at the level that we've been making for 20 years, requires a business case, because every time there's a big new commitment, people realize that's sort of locking in your participation for many decades to come. So they will want to see such a business case, and we can provide it, and let me outline. So don't be frightened by the word business, it just means an investment case. You're investing tax money. Any international project is going to need to tailor it, because the reasons why the Indian government might invest in a project like FCC as a developing country trying to build up a technology base would be very different from the reasons why the Swiss might invest in it. It's in their country, they're going to get a big return, or why the UK might invest in it. And it needs to be tailored, and we need to accept that. We've also seen a shift in priorities for science investment since the end of the Cold War. And the end of the Cold War is a great thing, and I'm not decrying that at all. But science used to be sellable in terms of cultural value, international collaboration at a time of tension, showing that a democratic system can make progress. And all of those things have been superseded or certainly eclipsed in the minds of those Treasury bureaucrats much more by what does it do for jobs? What does it do for national competitiveness in a globalizing economy? And those may seem a bit banal, those may seem a bit short-term compared with understanding the cultural value of understanding our place in the universe, but if those are the decision-making criteria that the people with the checkbooks want to use, we can certainly explain in language they will understand what a project like the FCC will indeed do. So here's a scientist doing science, and you will notice she is a girl, and I will talk about that later. And she is understanding the universe in the way that Harry has described, by building big machines and colliding particles together and using elaborate computer programs to find the new things that are made. Unfortunately, that requires public scale investments. Universities by themselves don't have big enough budgets to be able to build things like CERN. CERN is a treaty organization which member state governments contribute to, and that means government investment decisions are made. Now, much as we may wish it were otherwise, our governments are not philosopher kings in the Platonic ideal. They don't particularly value knowledge for its own sake. They value the technology and the innovation and the skills that come out as perhaps a side effect or perhaps integral to the realization of the projects. But they're not looking at the value of the Higgs boson, they're looking at the value of those magnets and the training and the inspiration. So let's talk about the technology and the innovation and the skills that come out of basic research. This may be a little bit like not selling the steak and selling the sizzle. That's an old 1950s advertising slogan. Sell the experience. Tailor your message to what the audience wants to hear. Scientists don't always like doing this. It feels a bit like salesmanship. It is salesmanship after all, but we are selling something that is of value. We're using the language that the audience understands. So the biggest economic challenges of today, if you were in that lift with the Chancellor of the Exchequer, globalization together with automation leading to fewer good jobs, leading to very unhappy people, leading to Donald Trump in the White House and Brexit and all manner of other things, Gilets jaunes protesters in Paris. There are big other problems that we cannot ignore, like climate change, and we must not ignore. But for political actors thinking about their next election, they're focused on this stuff right now. And projects like the FCC may seem a million miles away from low growth and stagnant wages in steelworks in Scunthorpe closing. But the reality is that investment in scientific and technological innovation, and specifically STEM skills, scientific, technology, engineering, and mathematics skills, economies that have an educated workforce are going to be able to withstand these kind of shocks much, much better. So what can the FCC or what can basic research do to help this sort of situation? They can develop transformative technologies, and they can attract young people into science and train them for the 21st century. In fact, the Institute of Physics did a study a few years ago that something like 90% of physics undergraduates in UK universities had originally decided to study physics because of an interest in particle physics or astronomy. The reason you're all here tonight, to understand the fundamental structure of the universe. This kind of science is an entry drug into a career or an interest or a motivation to understand science and technology and engineering, and those are skills that the UK economy needs. Something like 50,000 more scientific and technologically trained people per year based on the requirements of manufacturing industry. So there's a need for more people, and this is a way to encourage more into those very productive and useful careers. Now, you all know about the World Wide Web, technology, innovation in information sharing that was invented at CERN as a way to communicate in the construction of the Large Hadron Collider. You may not be so familiar that Wi-Fi is also a spin-off from basic research. The algorithms, the computer algorithms used to decode the Wi-Fi signal in a very radio noisy environment were invented for radio astronomy, in Australia it so happens, by a team of scientists who were trying to test one of the predictions of Stephen Hawking about black holes. So and the proof of this is that the Wi-Fi chipset in your phone pays royalties to the Commonwealth Science and Industry Research Organisation in Australia for the use of those algorithms. So it's not just a vague link, it's a real monetary benefit to Australian astronomy that this happens. So I can't promise that the FCC will deliver you a replacement for the World Wide Web or a replacement for Wi-Fi. There's a good track record of these kind of spin-offs, but what I can promise is that it will generate new, higher magnetic field magnets, and the original superconducting magnet technology is itself a spin-off of particle physics. Back in the late 70s and early 80s, the Tevatron accelerator at Fermilab in the United States was looking to build the first large-scale installation of superconducting magnets anywhere, and they placed orders with companies to deliberately stimulate the creation of an industry, to take steps to create companies able to build these things that didn't exist up till now. And that led then to the emergence of a multi-billion-dollar market for superconducting magnets driven by medical imaging machines. And so the commercial value of the medical imaging industry is several billion per year, and the value to all of us from having MRI scanners in every hospital is many times that in terms of improved lifestyles and healthcare. So if we think about a project like FCC, we should try and maximize those sort of impacts, and that means involving industry and key R&D packages and setting up places where that innovation can happen. And a really good example is just down the road from here at the Harwell campus. The European Space Agency runs a business incubation center here next to the Diamond Light Source, which provides help to commercialize technologies that have been invented and devised from the European Space Agency to make sure they actually get out into the market and make things happen. Zoopla, for example, uses a location technology, a location mapping technology that was part of the European Space Agency's innovation program originally. So something like this is a good example of how to maximize your economic impact. Small companies. We also need to think about how to attract young people into science. Well, you've already been attracted because you're here, and the Higgs discovery was a really good example of how one can do that. It was front page news, even in the Financial Times. And when I was at STFC, and in fact, the first time I met Harry was in putting together an exhibition at the Science Museum, which celebrated the Large Hadron Collider and what had been discovered, and we made sure to invite people like George Osborne, who at the time was influential, and introduced him to Stephen Hawking and Peter Higgs, and made sure that this got out to the general public, but also key decision makers like the people in the ministry. So we put a vinyl, we, STFC at that time, put a vinyl wrapping on the front entrance to the ministry that was responsible for science funding in the UK. So all the 2,000 civil servants working there would walk past a big picture of the LHC on their way into work, and I hope feel a little bit of pride at having supported that. And this was then picked up as part of the UK knowledge promotion in embassies overseas, and has had a real tangible impact. So people have talked about something that's called the Brian Cox effect, an increase in the study of physics in British universities after the Higgs and following the wonders of the universe and all of that. And it shows that you really can change the choices that young people make. And I don't want to sound patronizing, but I hope that the youthful faces smiling in the audience here are already interested in science. We need to reach out to the people who aren't in this audience yet. The public engagement program around the Higgs discovery reached more than half of the population of the UK in one way or another, through TV, through newspapers, through magazines, through all of the materials that we put out. So I would like to set a big goal for something like the FCC. If we set aside as little as 1% of the budget in the UK alone, we could spend £12 million on promoting science, which is much more than was ever spent on the LHC Higgs discovery outreach program. And so a good goal might be to double the number of girls taking A-level physics, which, as you can see from these charts, remains very low in comparison to the number of boys. The numbers of both genders taking the subject have increased, which is good, but this gender imbalance has not shifted, or doubling the number of engineering apprentices. And something like this in every one of the partner countries of FCC would, I think, be a good goal. So there we have a checklist, and I've very quickly and breathlessly tried to go through all of these reasons why investment in FCC is a good thing, and how you might convince skeptical audiences that it is a good thing, not just because the science is fascinating, but because it has tangible short-term benefits as well, and because it's affordable, and because you could imagine putting together a credible R&D plan to deliver it. So we know what we have to do. No one said it would be easy, but we don't do these hard things because they're easy, right? This is a many-decade project to build what will be, by many orders of magnitude, the largest science experiment that the world has ever seen, if it is successfully realized. And so we should not expect it to be straightforward, but we have to present a plausible route to success, and I think that's what we can do. And so finally, I'd just like to close with a quote from Daniel Burnham, who you may not have heard of, but he's a city planner and architect who was responsible for a master plan of Chicago over 100 years ago. And he famously said, "Make no little plans, they have no magic to stir men's hearts." So what we're trying to do with the FCC is certainly not make any little plans. Thanks very much.
Thank you. So, well, if you're anything like me, you're starting to feel quite sorry for any science minister that finds himself in the elevator with John. So we've got some chairs coming up. We're going to sit around the front here. So if you've got questions, this is your opportunity to ask them. And don't be shy. We've seen a huge, broad range of topics this evening, from fundamental particle physics all the way through to how you actually build an accelerator. Feel free to ask the hard questions of both of our panelists. And then at some point, I think if there are questions from anyone who's watching the YouTube live stream, we will also get those magically delivered. So who would like to start? Questions? I can't see very well. There's some people around with microphones. I can't even see the people with microphones. Okay, people with microphones, see who you can find. Yep. Yes, good start.
So, I know we're talking off with the word so. So, you had that chart, and then we only talked about dark matter, But then, we didn't talk about dark energy. So would you like to explain it for the audience, please, including me?
Very good question. Well, The reason I didn't talk about dark energy is because I don't know anything about it, and no one really does. I mean, it's unlikely, I think it's fair. I mean, that there are possible ways in which a machine like this could tell us something about dark energy, but it's quite unlikely. I mean, what we do know about dark energy is that the universe, well, we know the universe is expanding, and that's because it started with a Big Bang where it was small, and then it's been getting bigger ever since. We used to think that gravity should have been slowing the expansion of the universe down, so all the galaxies and dust and all the rest of it would pull the universe back together, and gradually that expansion would slow. What was discovered in the 1990s was that that expansion is actually getting faster, so the universe is inflating faster and faster and faster. And so we came up with a word called dark energy, which describes some kind of repulsive anti-gravitational type force, which is causing this to happen. As for what it is, there are lots of different ideas. I mean, one of the first ideas was that, well, actually, one idea is that it could even be the Higgs field, the thing that gives mass to the particles. That might have, early on in the universe, had the role of causing it to get bigger, so, or at one point early on in its history. Another idea was that if you take a bit of space and remove all the stuff, as I said, there's still some energy left, because all these fields, which the particles exist in, have what's called zero-point energy. So these are little vibrations, little jitters due to quantum mechanics, and you can add up all the energy that's stored in these little jitters and work out how much energy a bit of empty space has. The problem is you get a number that is 10 with 120 zeros after it too big. So that it's what's called the worst prediction in physics, and if dark energy was that, we'd all have been torn to shreds instantly and the universe wouldn't exist. So there are hypotheses out there that could be a field, or it could be vacuum energy. We haven't understood it properly, but honestly we don't know, and it's probably not going to come from a collider experiment in the near future, unfortunately.
So it might,
but that's sort of, you never know. It could be, that could be the thing, that the surprising thing that I mentioned, I guess.
I think we need dark energy for science budgets, something that instead of making them collapse back in themselves, at infinite expansion. Okay, right, who else have we got? Is there someone over here? I can't. Oh no, you were sitting down. I think you were sitting next to someone. Have you got on the balcony? Is there anyone up on the balcony who's got a question? Yes, someone on the balcony.
So you have your circular colliders like LHC, smaller ones, planned even bigger one. But you also hear about linear colliders in various other places doing various science. And why do you have one over the other? Clearly there's a case to have both, because both exist, so strengths, weaknesses, etc. Why for your next collider, why is it going to be a circular, for example? Yeah. Why not 100 kilometers linear?
So there is an obvious advantage in a circle that you can the beams of particles come back and collide with each other more than once. The extra cost that you have to pay for that is the magnets needed to corral them and keep them circulating. So there have been proposals, and there are proposals that will also come to this same strategy workshop for just a straight-ahead collider of electrons and positrons, which would avoid the need for exactly such a long tunnel, but it would still be about 30 kilometers long, and it would still be roughly as expensive. The major difference is it wouldn't have the upgradability to put the proton-proton collider in the tunnel later. So the precision science that Harry talked about of measuring the properties of the Higgs with great precision could indeed be done with this alternative approach. And there has been an idea in circulation for about more than 5 years. There was some interest in building such a machine in Japan, but that interest seems now to have cooled. There is also a concept to do something like that at CERN, and that will be considered as another alternative approach in the European strategy exercise which I outlined. So these are all credible ideas. They have an engineering deliverability. They can be costed. What they don't have is the potential to upgrade in the way that we've talked about here.
So on the topic of questions and who asks questions next, on the topic of women in science, I'm very keen that we have as many questions from women as we get from men this evening. So if you're a woman and you have a question, don't be shy. Please speak up, because we would like to hear from you. I think we've got a question somewhere at the back there.
Hi, so if we do discover some things about dark matter particles, what would you expect to discover? Are there any plausible predictions?
Well,
do you want me?
Well, I mean, so if we did, so are you asking sort of what could these particles be? What might we expect to see? I mean, so at the LHC, for example, a very popular idea until the LHC started taking data was something called supersymmetry, which is an extension to the standard model where all the particles get a superpartner version. They're called sparticles, and they all have very silly names. And the lightest, in a lot of these supersymmetric theories, the lightest particle had the right properties for dark matter. So it was electrically neutral, but it interacted with the weak force, which means that you could make them in a collider. So the signatures you're generally looking for in a detector, as I said, is you have your protons coming in, or your electrons and positrons, they collide, you get a load of particles flying, and then if you add up the amount of energy that you see in the visible particles, and you know how much energy you started off with, then you can see that there's some missing energy which was carried away by a dark matter particle. In terms of, I mean, there are lots of different flavors of dark matter. So a WIMP, these weakly interacting massive particles, they're the kind of the most sort of, I don't know, most studied option, where there are other things called axions, which are very strange, and they tend to have lower masses than WIMPs. So there's various different candidates. As for which ones we discover, I mean, we don't.
So I think that the key things you'd want to check, if you found something and you wanted to know if it could explain the dark matter that we see in telescopes, is how massive the particle was, how heavy it was, and how strongly it interacted with everyday stuff. Because that would tell you how many of them had been made in the very early universe compared with all the hydrogen and atoms that we're made of. And that would enable you to test that observation that about 27% of the known universe should be made of dark matter. And you might find something that looked like dark matter but didn't interact strongly enough, and then you say, well, there must be some other things going on there as well. So reconciling what we find in a future collider with what we see in telescopes will be one way to check whether what we found actually is dark matter in the way that we see from astronomy, or whether it's just some new particle that we need to connect to a whole hidden sector of new particles, as Harry said.
Yeah, I mean, and it's not just colliders where people are looking for these things. Like, it's so difficult. You find all these. The people I feel sorry for, actually, that there are people building detectors, and we don't know what this stuff is, but if it's not the thing that gets detected by their detector, they're spending a lot of years looking in the wrong place. And I was in South Dakota. There's a big mile and a half underground. There's a big dark matter detector of one particular type, and I went down there and I talked to the people. They showed the science. It's all very interesting. And then I noticed up in the corner there was a plush, fluffy toy unicorn, and I said, why is there a unicorn? They said, oh, well, if we go home in the evening and we haven't seen dark matter, we've still seen a unicorn. And I thought that was a very good attitude.
Yeah. There was also, I mean, WIMPs, people always laugh at the name WIMP, but we forget there was actually a competing theory with machos. And the idea was that you could either have machos or WIMPs, but machos have been ruled out long ago. So we're just left with WIMPs.
Yeah. Although, I mean, interestingly, so I don't know if you've heard of gravitational waves, which have been discovered a couple of years ago by these big L-shaped machines called LIGO. And one of the interesting things is that they've observed collisions between black holes, and the collisions they've seen so far are of black holes with quite unusual masses of about 30 or so solar masses of the sun, solar masses, so 30 times the mass of the sun. And that's led some people to speculate again that maybe dark matter could be a big population of, you know, sort of 50 solar mass black holes, which isn't totally ruled out in some kind of version of the theory. So it could be there isn't a new particle, and maybe it's something astrophysical that we haven't discovered yet as well. So there's lots of options.
I don't think that works with primordial helium density or something like that.
Okay, right, more questions. Someone
coming down the stairs.
Okay. YouTube questions arrive on a clipboard, apparently.
Right. They've been
okay.
transcribed.
Right. Here's a good question. Doesn't say who it's from. Are there any practical, foreseeable applications for the data that these colliders would generate? Is it going to do anything useful?
So, as I've said, the way we have to portray the benefits to short-term decision makers like politicians is to describe the technology impacts of the innovation that we need to do. Because the timescale for any application of the science itself is probably closer to 100 years, and that's way beyond the timeline that most of us will directly understand. But things like when the electron was originally discovered, when neutrinos were first discovered, nobody could imagine how these could have any practical application at all. Radioactivity, when first demonstrated, seemed like a curiosity. So we don't know is the honest answer. It's not going to be straightforward to see how you could use the Higgs in your daily life, but we know that special relativity and all sorts of esoteric science from 100 years ago is absolutely key to what we do. You know, the GPS that you use to get to this lecture tonight relies upon Einstein's special relativity being correct. And at the time when that was being tested scientifically 100 years ago, nobody could imagine that anything precise enough to ever require those level of calculations would ever be relevant to anybody's daily life. So we shall see, I think, is the best answer.
Yeah. Anything to add?
That famous, is it Faraday and George IV or something?
It may have been even in this, it may have even been here.
What is the use of this electromagnetic phenomena in the 19th century? And he said, one day, sir, you will tax it, you know, exactly.
So let's have any more from the audience anywhere. Where are the microphones at the moment? Somewhere up there. Was it one up there? Over there. Oh, I thought you were pointing at someone who had a microphone and making you work hard here.
Get your 10,000 steps on the Fitbit.
About the Higgs field, and how at some point in time it switched on and gave particles mass. Is there any possibility that it will like stop giving particles mass, or give them more mass, or change in some way?
I feel a disaster movie coming on.
Yeah. I don't want to frighten you, but yes. There's a possibility, and this was sort of this came along with the discovery of the Higgs, that the what we call the vacuum, in other words, the arrangements of the various fields that we know about, could be unstable, and that the Higgs field, if you imagine the Higgs field as like a kind of a ball rolling down a hill, that it's kind of rolled into a valley, but actually maybe there's a deeper valley somewhere else, so it could kind of fall to change to a different value. And this could happen. We know it's probably not very likely because the universe is still here. So if this is going to happen, it's probably going to happen very long time in the future. But through quantum processes, it could kind of, the Higgs field could tunnel to a lower energy state, and what that would trigger would be the formation of a little bubble in the universe where you had a different value of the Higgs field, therefore totally different masses of all the fundamental particles. That bubble would then expand and obliterate the entire of the universe. The good news is it would happen at the speed of light, so you wouldn't know it was coming. Yeah. So,
and as you said, the universe has been there for 14 billion years, so this isn't. Well, yeah. Let's see if we get home tonight.
That's one of those terrible things where you can't prove it's not going to happen.
Exactly,
you can only show it hasn't happened yet. Right, somewhere up. Microphone up here somewhere. Yes, on the front here.
I was determined to not start my question with the word "so." So, by comparison, how does a supercollider at the at CERN, compare to supercolliders elsewhere in terms of the funding menu? So, how does it compare to, for example, the Chinese proposed supercollider?
Yeah. So I was expecting somebody would ask. There is an ambitious group of scientists in China who have had at least the concept of building something like the FCC purely as a Chinese project. Doing it at CERN has the obvious advantage that you can use the existing research infrastructure there, the Large Hadron Collider as the feeder, the injector, and that reduces the cost. CERN also has a very stable institutional structure. Let's say it's a treaty, and that means you're pretty much guaranteed that the countries that are members of CERN will continue to contribute to it. There is a lot of confidence in the civil engineering ability of the Chinese to build big tunnels and high-speed railway things and stuff like that, but I'm not sure that they have the scientific manufacturing capability to build 100 kilometers of magnets. Now, that would be part of the business case that the Chinese Academy of Sciences would say, okay, well, we would create then that capability, and that would attract young people into science in China. And to some extent, you could imagine them making the case to their own government along the lines that I just made here. But it would be a very expensive project for a single country to undertake, even one as populous and prosperous as China is hoping to become.
Anything to add?
So I would like to invite the Chinese to be part of an FCC project. I think that would be a way that they could learn how to do science at the global scale. And that would be a good way to promote, let's say, a valued continued collaboration with China in times of international tension, which is a good lesson from the Cold War. There was always good collaboration between Soviet and Western scientists, even during the most tense periods of the Cold War conflict. So right now, anything that can build international collaborative trust is a welcome thing.
More questions? Oh, many more from the balcony? Can't really see anything anywhere up on the balcony. Over there somewhere, yes.
Funding decisions in this country in the last 8 years have all been about cuts. How do you convince funders to make a commitment that can't be cut? Once you've made the commitment, it's 30 years, and you can't cut it without completely dropping out.
Can you do that?
Well, so as I said in the answer to the previous question, the institutional framework of CERN helps because as a treaty organization, it is much harder for any single member to vary the level of its membership. The CERN Convention lays down the amount that you need to pay each year as a fraction of the total budget. So if the total budget is agreed, the UK's contribution is set. That doesn't mean everybody's happy to pay it, but it means it's hard for them not to. A project like this has to have broad cross-party consensus and consensus from sectors outside, not just individual politicians. Otherwise, it will never survive. And that's one of the lessons from the superconducting supercollider in the United States. But my experience with British politicians over the last few years has not been as negative as you say. There is a willingness a cross-party willingness to see investments in science and technology as a good thing. That doesn't mean that every project in science and technology is automatically going to get funding, but it means they're not looking to reduce the overall science budget anymore. In fact, there's a commitment to grow that. And so it's not a hostile environment in which to be making a case for science, but that doesn't mean you get an easy ride when you're proposing a big long-term commitment. So the sort of arguments that I outlined have been successful in securing UK participation in other big science projects. And what we're talking about here would mean continuing roughly the current level of investment in CERN for many decades into the future. So it's not asking for more money, it's asking for many more years of contribution at the present level.
Is it right? Is it Austria tried to leave CERN a few years ago, I think, and then reversed its decision because it found it
an Austrian science minister had a little bit of a brain fit. Yes.
Right. Okay.
Well, no, okay, for smaller countries without a big history of contributing substantially to the project, you should always be able to ask that question and reassure yourself that you don't want to pull out.
So I think we've got time for 2 more quick questions. So one over here, somewhere. Yep.
My name is Juana, and I would like to thank you for your presentations and dedication and hard work. As an advocate for innovation and future development, my question to you all is, how can we contribute to support your work, and what is your call to action for us in here and at home?
Call to action.
Right. Wow. Okay. Well, but you could do a PhD in particle physics or engineering. I suppose that would be very helpful. I guess these projects, I do a lot of public engagement work, and I think, you generally, there's the people I speak to are always very enthusiastic about these projects, but that's because the only people that come to the events that I do are already interested. So I guess, if you can encourage your more skeptical friends to come along or learn something about physics, I guess that would be a helpful thing.
Yeah.
All right.
Yeah, spread the word. These projects ultimately require a broad consensus in the public that they are good things to spend money on. And there are no better advocates for it than other members of the public talking to their friends, sharing opinions when you meet random taxi drivers, skeptical audiences who might not show up for an event like this, but those you come across in daily life. It would be great to spread the word about this project and just about the value of basic research in general.
Okay, last question. Somewhere up there? Yeah, there.
I wonder if you agree with something I would think, that we've been saying that fusion research has been 25 years in the future before we get a reliable fusion power station. Is the funding for FCC and fusion research about right, or should we be spending more on fusion research? You talked about ITER. What follows on from ITER, and is that in conflict with FCC? That's one question. The other one...
Oh, I said one question. I said last question.
The other thing, the initial expansion of the universe, we don't understand that, as I understand it. And does FCC make any contribution to our understanding of why there was this sudden inflation at the beginning of the universe?
Okay, quick answers from both of you.
Well, I honestly don't know the answer to your second part of your question. I mean, I think, as I said, there are potential connections between what's called the inflation field and the Higgs field. So studying the Higgs field could potentially tell us something about that. But I have to admit, I'm not an expert on that sort of topic. I don't know if John knows.
So as far as fusion is concerned, what I understand is now the schedule at ITER is science and engineering driven, not limited by the amount of money that they've got. They've got real hard engineering challenges to solve, and they're solving them as fast as they can, and good luck to them. Yeah, I mean, what Harry was saying about the Higgs field would have driven an expansion of the universe according to our current theories that would have been way too fast and we wouldn't be here. So particle physics has to say something about that, but it has to explain what drove the expansion and why it wasn't the Higgs. So there's a lot to learn about the Higgs, which is why we need to study it in great detail, and there's a lot to learn about all the things we don't yet know, which is why we need a new higher energy machine to explore them directly.
And on fusion, it's not just the big projects who are in that game. So that is turning into a very interesting space in the next few years. So keep an eye out for the smaller projects.
Future presentations here.
Yeah, I'm sure the RI will be covering them all. And that is probably a great place to end on the 220th birthday of the Royal Institution.
Hooray!
Thank you for coming along. Please thank our two fantastic speakers. Well done. I hope we'll be seeing you back here soon for even more exciting science. Thank you for coming along.
Thank you, Helen.